little bit about me, if you haven't run into me before. I've been a ham since about 72. Got my license when I was in high school after finding a QST in the county library and deciding that was for me. Um, and then that led to an engineering career and various misbehaviors, and I wound up teaching and then writing for the league, and I was the editor of the handbook and the antenna book and all three license manuals there for a while. So I felt like I had the green and the blue on the monopoly board, but I'm sort of retired from that now and giving some talks, and tonight's talk is going to be on the ever popular end-fed half-wave antenna, where it comes from and how it works, why it works, really. So we're going to go through the end-fed half-wave family tree. So give you an idea of what this antenna is like and where it comes from. It's used by a lot of people, particularly portable in Parks on the Air, which is an amazing program. Summits on the Air, I have one here in the city lot, and it does amazingly well. It punches above its weight. And so we're going to talk about this end feeding business. It's got a lot of mythology associated with it, so I'm going to try to demystify it a little bit. And then we're going to talk about this transformer business. All of them have a transformer, a magic box at one end, referred to as the transformer. So we're going to talk about that and why that's so crucial to this antenna. And we'll get into a short discussion of counterpoise and sort of a poise counterpoise discussion and what that is. And then we'll go through putting the end-fed half-wave to work and making your own. So without further ado, the family tree. Okay, way back, the very first antenna ever used was a center-fed half-wave dipole by Professor Dr. Heinrich Hertz in its experiments from 1885 to 1889. It was about 1 meter long on a side, and you can see the little spark gap in the middle and a couple of large spheres on the end, and that's what he used to demonstrate that the electromagnetic waves that were predicted by Maxwell in the 1860s did in fact exist. And he did some experiments with reflecting and generating and receiving. He was able to generate a wave on one side of the lab and get a little spark to jump across the spark gap on the other. You can learn more about this on the Wikipedia entry. And somebody asked him, so you've discovered these amazing waves here, Dr. Professor. What are they good for? And Hertz replied, nothing, I guess, literally. So things have progressed, and really the center-fed half-wave dipole is still the best bang for the buck in ham radio, in my opinion. There's no antenna that is easier to make and wants to work more than a half-wave dipole. So it's good stuff. If you wind up with what you think is a compromised situation and all you can put up is a dipole, you'll be surprised how well it works. It's always a great backup antenna. All right, so continuing, what happens when you excite the half-wave dipole? What does the word dipole mean? It comes in two parts, literally, and in the word, di means two, and pole means polarities, voltage polarities, one positive and one negative. And as you can see at the diagram at the bottom, the dashed line shows you the voltage along the antenna. And on one side, positive, on the other side, it's negative. And then these reverse every half cycle. Okay, it's also resonant in this particular drawing. And the current through the antenna and the voltage are in phase everywhere. Now it looks like they're 90 degrees out of phase in this drawing, but this drawing shows the magnitude, means how much voltage or how much current is present. And you've got a feed point in the center, and at that point you have low voltage, meaning there's not much voltage driving current back and forth there, but the current is at a maximum there because this is a resonant circuit, and so it's like pumping a swing back and forth. It's also like guitar string. I'm sure we have plenty of stringed instrument players out there, and this is basically a guitar string on its fundamental when you pluck it, and this is the lowest frequency. The current or the displacement of the guitar string is a maximum at the middle, and so basically this is the lowest frequency that the dipole wants to work on as a resonant antenna. At the middle, you have low voltage and high current. That means you have low impedance. Impedance is just how hard you push to how much you get. And so the pushing is the voltage and the current is the getting. So at this point in the middle where you have a minimum amount of voltage and a maximum amount of current, that's where you have low impedance. So if I'm exciting this antenna on its fundamental, well, what if I want to use it on other frequencies? I can extend this antenna in segments of a half wave, just connecting them end to end. You can see my original feed point in the middle here. Let me put my cursor right here at the little red circle. And this is the original antenna right here, the original dipole. And I've added two more half waves, one on each end. Okay, well, the current just keeps flowing. Here it is, a maximum, and then it goes through 0 at the ends, and then it goes through another maximum, but in the other direction. And so if current is flowing this way in this dipole, it'll be flowing this way in the other dipole. Same over here, this way. Okay, so here at my original feed point, I've got low impedance, as we learned before, low voltage, high current. Well, at the end, I've got high impedance, which is high voltage and low current. And then another quarter wavelength along this piece of wire, I'm back to low impedance. So there are multiple points along the antenna with low and high impedance. And you can see that this particular antenna is being exactly the same as if I operated the original half wave antenna on 3 times the frequency. So the half wavelength was then a third of the size. So I get the same exact performance as you can see here. So it's resonant on the harmonics, whether it's even or odd, as long as the voltage and the current are in phase, it's resonant. And resonant doesn't mean anything about the feed point impedance, doesn't mean 50 ohms, it just means that the voltage and the current are in phase. But on the harmonics, it's no longer a half wave and it's no longer a dipole. You're just exciting this thing on a harmonic. And it's the same way on guitar strings. If you pluck them, you can hear not only the fundamental, but what's called overtones in the audio world that are the harmonics. So here's a very nice drawing from ON4AA, and it's kind of complicated, but it shows above this antenna line, this is the antenna right here. All these lines are current, and on the 2nd, 4th, 6th, and 8th harmonics, these are the even harmonics. These are the odd harmonics down here. We're just showing the current, not the voltage right now. So here's the fundamental. It's just like we saw, one big current half wavelength there. And then on 3, what we saw in the previous slide, you have 1, 2, 3 current maximums. And then 5, you have 5 current maximums and 7. Well, they're distributed a little differently along the antenna on the even harmonics. Here's our second harmonic. You have 2, 1, 2. And for the fourth harmonic, you have 1, 2, 3, 4. Okay, so for the odd harmonics down here, you have low impedance in the middle. So if I connected my feed line here, I would see low impedance on the fundamental, the third, the fifth, and the seventh harmonic. And that's in fact what you get. If you put up, say, a 40-meter dipole, you can use it on the third harmonic, which is 21 megahertz. You can use it, if we had a ham band, you could use it on 35 megahertz and so on and so forth. But on the second harmonic, I have high impedance and high voltage and low current, which means high impedance in the middle. And that's what you would see. You tried to use your 40-meter dipole on 20 meters, you would have a high impedance in the middle if it was being fed in the middle. So you can see the different structure of the current here on the antenna at the different harmonics from the first fundamental all the way up through the eighth. Okay, and if you look really closely, if you cross your eyes and unfocus a little bit, you'll see that right along here, about a third of the way along the antenna, the impedance is all about the same. The current's kind of moderate, whether it's going backwards or forwards, we don't care. And so this point, all these different harmonics have a similar impedance. They're not the same, but they're similar. And so if I came up with a device that could match this similar impedance to 50 ohms, well, I might be able to excite that antenna on different bands. So that is, in fact, what we are doing with the off-center dipole. What you find is on this antenna that you're using on the harmonics, this half wavelength on the fundamental, there are points with a similar, what I'm calling impedance of open off-center fed dipole, C, OCF, on multiple bands. And that impedance, that similar impedance, is somewhere between 100 and several hundred ohms, depending on where you connect the feed line exactly. And at that point, you use an impedance transformer to reduce that impedance from 100 to several hundred ohms down to 50 or 75, whatever type of coax you decide to use. And so those impedance transformers are typically 2 to 1, 4 to 1, 6 to 1. For example, if you had a point at which the impedance was close to 300 ohms on several bands, and you had a 6 to 1 impedance transformer, that would knock it down to 50 and give you a good SWR. But you'll find 2, 4, 6, and 9 to 1 transformers used based on where that feed point is located. So you basically mess around, is the technical term, and find a feed point location so that your SWR with the impedance transformer connected is acceptable on multiple bands. And what we have over here at the right is a drawing, W4RNL, silent key, but LB Civic generated a huge amount of papers and all sorts of articles. You can Google W4RNL off-center dipole and find this drawing. You have the feed line here, and then you have various ratios. Here's the overall length. That's going to be a half wave length. And then here you have half the length, and then you have, depends on where you cut it, there's lots of different ratios here. Okay, so if I have a ratio of D1 to L, let's go back and look at that. D1, this part, to L, in other words, what fraction of the antenna length is this feed point placed at? At 29% along the antenna, you can use a 4 to 1 transformer and use this antenna on 80, 40, 20, 15, and 10. This is for an 80-meter half wavelength dipole. It's about 100 and something feet, 120 something feet long. And that's a typical design. You'll find lots of those out there in various books and as products. Other common designs if you put it exactly, D1 to D2 is 1/3, in other words, 25% along the antenna. That's another common design. They use higher impedance. Remember, when you get closer to the end, you get closer to high impedance. And another common design is 20% from one end. So basically, you mess around, find a spot that's right for you and your impedance transformer. And you got to remember that this isn't guaranteed to function exactly, because the height above ground of the antenna affects how the antenna works, and how's your ground conductivity. Somebody in a swamp is going to see different results than somebody in the desert. And what about nearby buildings? And is this thing slanted a little bit, and all this kind of stuff? So it's not a guarantee. You may have to experiment, and hams get pretty good at tuning and adjusting antennas. Going back to 29% offset, here's what we're looking at, 28.9%. Here's a graph of percent offset at the bottom. Here's a graph, SWR related to 200 ohms. In other words, you would use a 4-to-1 transformer at this point. And you can see it right here, right in here. We wind up with an SWR between about 1.9 and, this is about 1.4. So that's a good spot, and that's why 29% offset is common. Okay, there is one other point along this piece of wire, this half-wave antenna, where the impedance is similar on all the bands, and that is the end. Out here at the ends, you have a very low current right there and right there, and you have high voltage. So you're pushing a lot, but you're not getting very much current. You have high impedance. So the high impedance is another common point along this antenna. And then the light goes on. Aha! Okay, so typically the Z at an end-fed point, Z sub EF, at the end of an antenna like this on HF, it ranges from about 1,000 to 5,000 ohms. Excuse me. This can vary quite a lot. High impedance points are affected by capacitance. It does not take many picofarads to really affect a high impedance at RF, particularly height above ground, the nearby conductors like antennas, conductive surfaces like buildings, things like that. That tends to load down this impedance. So it's really very hard to have an impedance at 5,000 ohms or more at RF, because there's all this distributed capacitance to the ground and all these other points. So typically your impedance is going to be between 1,000 and maybe 3,000 or something like that, but it's really hard to get it all the way up to 5,000 and higher. Now, there are difficulties with feeding an antenna at this point. Back to our guitar string analogy, if you pick a guitar string in the middle, it doesn't take very much to get a lot of deflection of the string, and it's easy to make it loud and have it vibrate quite a lot. But if you move all the way to the end, down by the bridge, I'm a mandolin player, so I know about this. If you move all the way down by the bridge and pick the string there, it doesn't move very much. For the same amount of picking, you get much less flexing of the string, and that's like an impedance of the string. So when you're trying to apply energy to an antenna or a guitar string at the end, it just has a high impedance. It's tough. So as we just saw on the previous drawing, you also have high voltage. So you have to be careful about how you're connecting everything together down there. You have to keep it away from foliage and bare feet and all that kind of stuff. And then, as I said before, capacitance to ground, to anything else, to you, will affect the antenna impedance at this point. Here's some typical in-fed, this is also called voltage feed. because you're trying to apply power where there's high voltage. Here's some traditional antennas that old timers will recognize, and even some new timers. Over at the left, we have the ZEP, and this was called ZEP because they used to use it on the Zeppelin airships. They would hang these things off one end of the airship, and this part would be a half wavelength at the lowest frequency operation. Sound familiar? And then they would feed it with tuned feeders. They'd just let it hang down below the airship and have the tuning circuit up in the transmitting room. That was called an infed ZEP, or just a ZEP. Here's a half square. If you take a full wavelength of wire, these dimensions here are for 80 meters, and you make a quarter wave go up in the air, and then a half wave along, and then another half wave over here. What you have is two currents over here and over here that are in phase. You have to feed it at one end, or you can feed it in a corner, and that's called current feed. This is where the high current point is. So you wind up with current going up here and over this way, and then it reverses. So it's going up here and this way over here. This is another high impedance point in the middle. It's called a half square. It's beginning to get popular with the summits on the air folks because it only takes the one pole, and on 10 and 15 meters, it's a pretty manageable antenna. Here's the bobtail curtain, which is like two half squares back to back. Here's a technique for feeding these things. You make a resonant LC circuit, you adjust it to resonance with the capacitor, and then you tap along the coil until you get your best SWR 50 ohm feed line to the transmitter. And the bi-square, if you can see it over here, it looks like a loop, but it's not. It's two full wavelengths of wire pulled into a diamond. So this is a half wave, and this is a half wave, and this is a half wave, and this is a half wave. This is a high impedance point down here, and you use typically open wire feed line. So there's four different in-fed antennas. Okay, now here's a revelation. The half-wave dipole that we saw in Dr. Hertz's office, the off-center fed dipole, and the in-fed half-wave dipole are all the same antenna. They're exactly the same piece of wire, they're the same length of wire, and they radiate all just the same. All you're doing is moving the feed point around to where it's most convenient for you. If running the antenna with a coaxial feed line up to the center is what you want to do, then you've got a half-wave center-fed dipole. You can have an off-center fed dipole, or you can have an in-fed dipole. They're all the same antenna. They have the same gain, they have the same radiation pattern, and so there's no magic here. One of these is not suddenly tremendously magic and performs way better than the others. It's a matter of convenience and your circumstances, what works for you. All three of them have different bugs and features. If you are going to use the off-center fed or the in-fed, then you have to have a transformer, so you have to worry about transformer loss and weight. What about feed line loss? If you're going to use a center-fed antenna on an even harmonic where you have a big mismatch, you're also going to have a lot of feed line loss. How many supports are you going to use with things? Do you just have one support? Do you have two? Are you going to use a tree or a building or whatever? And if you're hiking up to the top of a mountain, weight is also important. So you've got to look at all of these different things and weigh them together and decide which one of these configurations is going to be the best for you. But they're all the same as far as the RF that gets radiated and received. They're exactly the same antenna. The key to a good in-fed half-wave design is that transformer. And there were a lot of attempts to use in-fed antennas in various ways. And what really made them take off is a good transformer design. You had the right materials, the right turns ratio, the right type of construction, and suddenly that became a convenient antenna for everybody to use, and a lot of people are using them. It's important to pick the right impedance ratio for the transformer so that you wind up with an SWR that is also reasonable on the bands that you want to use the antenna on. So the turns ratio is fixed. You're not going to go out there and unwind the transformer to change bands. So what you do is you pick this in-fed impedance that you're going to aim for somewhere between 1,000 and 5,000 ohms. And if you scratch an engineer, they'll pick the geometric mean as the first calculation they try. And what that means is you multiply the two numbers together and then take their square root. The geometric mean of the range of impedances that we're talking about, 1,000 to 5,000 ohms. 1,000 times 5,000 square root is 2,236 ohms. So your optimum ratio here, if you're aiming for 2,236 ohms, would be a 45 to 1 transformer. Well, that's kind of a little hard to build, but it's conveniently close to a turns ratio of 7 because your impedance ratio is the square of the turns ratio. 7 squared is 49. So that's pretty close. Let's see what we get. If I have 1,000 ohms, then I divide that by 49, I get 20.4 ohms, and my SWR is 2.451. At the other end of the range, 5,000, I divide that by 49, and I get 102 ohms, so my SWR is 2.04 to 1. And 2,500 ohms, which is about right in the middle, if I divide that by 49, I get 51.2 ohms, so my SWR is right down 1.02 to 1. So this gives me a pretty good span of impedances of the antenna, and it gives me workable SWRs. Either I can live with it directly, or I can certainly use a radio's internal tuner to flatten out 2.5 to 1. Let's talk about this transformer a little more. The guy that really made this work and put out the information so that everybody could start enjoying this design is a guy named Steve Dick, K1RF. Isn't that a great call? Steve, if you go out and you just Google Steve Dick K1RF or just K1RF and in-fed half wave, you'll find his presentation, which is really very good. So what's the secret sauce here? First of all, use a toroid ferrite core, and it's important to use the right material, type 43. This is, if you look at it, here's the winding and that goes out to the antenna. All of the energy in this transformer goes through the core. This is not a ferrite choke antenna where you're simply using the ferrite to create a high impedance for common mode on a feed line. All of your antenna is going to go through the core. So you have to pick a core with a mix, meaning a type of ferrite that is not lossy at the frequencies that you want to use. Now, ferrites have sort of a Dr. Jekyll and Mr. Hyde characteristic. Over some frequency ranges, they're very lossy, and that you can use them to block common mode current. They create a resistive impedance, and that's good for RFI control and making a transmission line choke and that kind of thing. And then in the other part of their frequency range, they will store energy, so they make a good inductor. And so at some frequencies they act like a resistor, and then they gradually change over to an inductor. And we're going to use this ferrite type 43 at HF, where it acts mostly like an inductor. It doesn't start acting like a resistor until you get up into the low VHF range. Most of the little ferrite beads that you see on USB cables and things like that, monitor cables, that's type 43, and it's there to block emissions common mode emissions up in the VHF range. So we're going to use a ferrite core type 43. The most common design is 2 primary turns. See that in red down here. 1, 2. Each pass through the core is 1 turn. And then the secondary turns are in blue, and there's 14 of those. So the ratio is 14 divided by 2, it's 7. That gives us an impedance ratio of 49:1. Now you see this little crossover thing here. There was some discussion about, is that electrically important? Does that really change the electrical characteristics of the transformer? The answer is not very much. What this is handy is, what this does is allows you to put 14 reasonably spaced turns and have the output be on the opposite side from your input. And that happens to be a convenient way to construct stuff. Most designs will use, for 100 watts or higher, use number 14 wire, twist the primary and the secondary together. At this point, you're going to use enameled wire so they don't short directly together. And that makes a really good coupling between the input and the output windings. And what's this guy doing down here? This little 100 picofarad thing. What the heck is that? Some designs use 100, some 150. I've seen them as high as 300 picofarad. The point is to compensate for the inductance of this transformer. It does have some leakage inductance. So if you don't compensate for that, as you start getting up to 15 meters, 12 meters, 10 meters, that inductance starts to act like a reactance, and it screws it up, the transformer action. That's a technical term, screws up. And so if you measured SWR, what you'd see is a pretty good SWR, but then it would start going up. And a good way to test these transformers is just to make yourself a 2500 ohm resistor and then measure it with your antenna analyzer, and you would see down at 80, it's just fine, and then all of a sudden it starts going up. But if you put this capacitor down here across the input, well, by golly, it negates the effect of the leakage inductance and flattens out your SWR. Here's a schematic of it. Here's 150 picofarads. You want to use the 3 kilovolt, even if you're running low power, you want to use a high voltage capacitor because they are low loss and can handle a little current if they have to. So here comes your input coax to a SO239 probably, and here's the winding of the primary 2 turns. And then here's your ferrite core. These 2 lines means it's a magnetic core, and 14 turns on the output. And here's where your wire attaches. But wait, where's the missing current path? You come over here and you can see this. Here's the 2 turns of the primary, and they're twisted together with the secondary, and it comes up here, goes across the core, goes over here, and this is the output. But where's the rest of the current path? Sure, you've got an antenna out here, but the current has to go somewhere. It's got to complete a loop. Current only flows in a loop. So where's the rest of the current path? Well, current has to go somewhere. So W7EL, if you've used EasyNet, that's its author, Roy Llewellyn. He analyzed an end-fed wire. And here's your antenna, and it's fed at the end. And he constructed a feed line of 2 close together wires with the power source down here. And he had EasyNet draw the antenna current on here. And what he found is the missing current is flowing on the feed line. So if you go through and add all these things up, the common mode that flows on both conductors of the feed line here, that's your missing current. So the feed line is actually part of the antenna. You really can't just feed the end of something without making sure that you have a path for the current to flow in a loop. Okay, so but I use coax on this, and I've got an impedance transformer. Um, where's my current path there? Okay, well, if you're not going to put it on the parallel wires here, then maybe you've got a ground screen. Maybe you've got some chicken wire or some radials laid out, or it can just be the coaxial cable shield. Remember that the outside of the coax shield is electrically different at RF from the inside and the center conductor. So the outside is like a big fat wire that's connected to your feed point. You could put a counterpoise wire out there, just 10 feet of wire, lay it on the ground. You could connect it to a ground rod if you really wanted to, but you've got to give that current some place to go. Up through the antenna, it gets radiated, it induces a current that flows back toward the feed point. So you've got to have that path. All right, so how do we do that? In this particular design, there's a connection between the two windings. And if we go back, you can see right here, this little piece of wire right here connects the ground terminal and both wires in the primary and the secondary with the shell of your SO239 connector. That's where, that's it right here. And so that creates the missing current path. So you've got current in the antenna, it gets radiated out and it gets picked up on this stuff and it comes back to the transformer. So you've got to have something to complete that current path. Well, let's talk about the counterpoise for a second. What is a counterpoise anyway? It's a very old term in radio. If you go back and you look at old articles about, you've seen these giant wire contraptions and everything, and they have these big radial screens. They look like radials, but they're not on the ground. They're up in the air. What they make is a big capacitor that couples to the earth. Remember, amateurs used really long wavelengths at the beginning. It wasn't until we got shooed off to those useless wavelengths below 200 meters that the antennas started getting manageable in size. But a lot of things are called counterpoise. And so you hear people refer to counterpoise wires and counterpoise screens and counterpoise radials and all that. Okay, the whole purpose of a counterpoise is to lower the impedance at wherever it's attached, okay, in the antenna system. And all it does is couple an antenna to ground. That's its whole point, is to couple part of the antenna system to ground. If you can't connect it directly, then you build one of these things, or maybe it's your coax shield, maybe it's a wire, maybe it's some chicken wire, and it couples the antenna to the ground without a direct attachment. And that completes the antenna. And that's what's happening with your in-fed half wave. The counterpoise, whatever it is, whether it's your coaxial shield or actual wires, it's just completing the antenna. So when you say, oh, I've got an antenna that's 130 feet long, and then I've got a 10-foot counterpoise wire, what that means is you've got a 140-foot antenna with 10 feet of it connected on the other side of your feed point impedance. So the purpose in the in-fed half wave is that counterpoise function lowers the impedance a little bit. So you're not right at the end. You're back from the end a little bit, and it stabilizes the feed point impedance so it's not varying wildly with moisture or time of day or the wind or wherever the antenna is blowing around. It just stabilizes things and lowers the impedance a little bit. So let's see a typical installation. Here's an in-fed half wave. What can you do to provide the counterpoise? Most of the time, you can just use your coaxial feed line. You don't need anything else. The feed line is going to be 10 or 20 feet. It's going to lay on the ground. The capacitance between the ground and your shield is going to be perfectly sufficient to act as a counterpoise here. So you really don't have to go to great lengths. Some people say, oh, well, I'm going to put a choke bell in here to keep RF out of my station, or I'm operating close to this antenna and I don't want a lot of RF lighting up my computer and all this other stuff. So they put a choke bell in there, and then they find out, oh, this antenna doesn't work anymore. Why? Well, you just choked off your counterpoise. So you've got to replace it with something. And the most common thing is just a counterpoise wire laid on the ground, something less than a quarter wave. This is not a resonant wire. It's not a quarter wave radio or anything like that. It's just enough wire to lower the impedance a little bit and stabilize it. That's it. It's going to be open at the end. It might have high voltage on it. And if you lay it on the ground, I guarantee somebody's going to step on it. Might be you. And don't ask me how I know that high voltage and bare feet do not mix. Okay, so you got to be careful about that. Some people drive in a ground rod, perhaps in a permanent installation. You might want to put in a ground rod there. Maybe you use it for grounding the antenna for lightning protection. Bear in mind that for portable operation, like in parks and things like that, the rangers are not happy with people pounding in ground rods, and a lot of places absolutely forbid putting anything in the ground, including short tent stakes and everything else. So know the rules before you do that. The ground rod will help, okay? If you have a permanent installation, maybe just burying your coax, just slit the ground a little bit with a little spade or something and poke the coaxial cable into that slit, tamp it back together, and you'll never see it in a couple of weeks. Never see it again. Get direct burial cable and that'll be fine. So you can use your coax feed line, you can use a counterpoise wire, you can use a ground rod. Feel free to experiment. You can also put a screen out. And I'll tell you about a neat application for the screen and how to get one more band out of your in-fed half wave. But we'll get to that pretty soon. Let's go back to that transformer. I want to give you some examples here. You find in-fed half waves they're available as products. They have everything from 9-to-1 to 81-to-1 transformers. That's a turns ratio of 3-to-1. Let's see, 3-to-1 for this one to 9-to-1 for this one. And they all work to some degree. And depending on how you install these things and where you install them, a 9-to-1 might work, an 81-to-1 might work. Mostly a 49-to-1 is the most widely applicable. Okay, so you know that the impedance at the end of the wire is going to change with frequency. It's affected by ground and height and nearby conductors. So I went and took a spreadsheet and I said, okay, if my load impedance takes these values, 1,000, 1,600, 2,500, 3,500, 5,000 ohms, and I take these different types of transformers, 3-to-1, 4-to-1, 5-to-1, 6-to-1, 7-to-1, 8-to-1, 9-to-1, so that I get impedance ratios of 9, 16, 25, 36, 49, 64, and 81. And I plotted all of these on this chart. And I said, okay, what SWR do I get out of this transformer? Well, here's the 3-to-1, and I get a pretty good impedance at 1,000 ohms, but as the impedance goes up, so does the SWR. So I wouldn't think a 9-to-1 would work very well here, except down around 1,000 ohms at the end of the antenna. And progressively, we won't go through all of these. Here's a 9-to-1. It doesn't seem to want to work very well at 1,000 ohms, but it's pretty good at 3,500 or 5,000. Well, guess what? Which one, this light blue one here in the middle, that one has the best SWR over the entire range. It goes from a little bit above 2, 2.4, down to about 1 at 2,500, and then back up a little bit. to just over 2 at 5,000 ohms. So that's why you see the 49-to-1 or 7-to-1 turns ratio transformer. It's the best compromise over the expected range. You may have special circumstances in your installation that mean you might want to use the 1,000 ohm impedance and use one of these transformers. Or maybe you've got a really high impedance antenna, so you might want to use one of these transformers. Don't be afraid to experiment if you're buying your materials and making your own antenna. That's half the fun, although you might think it's not fun at the time. Okay, so what makes this in-fed half wave so popular? It's really useful for portable operation and in low visibility home stations. It's efficient. It's a half wave dipole. Okay, there's no coils, there's no linear loading, there's no folding, there's no magic jazz. It's not complicated mechanically. It's very light, so if you're going to carry it up to the top of Mount Podunk, it's not going to weigh you down. And it only requires one support. A lot of people like to install it with the transformer down here right by the transformer, and then just run that wire up to either a fiberglass mast or throw a line over a tree. A lot of parks won't let you do that either, so you got to know what your circumstances are. There's a 160 meter version of these things. It's about 260 feet long. That's kind of long for backyards in general, but the 80 to 10 meter version, it's 132 feet. So you get some up and some over, and if you've got a good sized tree in your yard, this might be the antenna for you. As a matter of fact, this is what I have at my home station here in St. Charles. It fits right in the backyard. You can also read the manual of the antenna. If you cut the wire and you add a series capacitor of a few hundred picofarads right there, you can change the resonant frequency up to 75 meters. So perhaps you're an ARES guy and you want to operate on 75 meter phone for emergency communication nets or whatever, you might want to add that series capacitor. You can, now here's the part I was going to tell you about how to get one extra band out of your antenna. Well, you know, this capacitor that you've got, you can put it across an insulator, and if you lower the antenna and replace the capacitor with a jumper or just short out the capacitor, then you can go back to 80 meters. So with a little rope work, you can change between 80 and 75. But notice that this thing's 132 feet long. What other band is that resonant on? Where have I seen that number before? 160 meters, that's a quarter wavelength. So what you do is you stretch out a ground plane underneath, you disconnect the impedance transformer part, and you drive the antenna directly from your coax, and it will act as a quarter wave ground plane. Now, it might be bent over a little bit or it might be slanted, but let me tell you, this wants to work. A full-size antenna just wants to work. And I work lots of stuff with my 80 to 10 in-fed half wave disconnected from the impedance transformer and driven it directly. Actually, I use a series 2000 picofarad capacitor from World War II. It's this big old mica thing. And it's great SWR. I've worked all over the United States from Missouri. That's typically how I get on for the ARL 160. If you don't have 132 feet, or maybe you're talking about backpacking or for camping or just a day's parks on the air activity, there's a 40 to 10 meter version that's 67 feet long, and that's great. And you can add a loading coil for this thing and a little extra wire, and then you can also use it on 80 meters. The bandwidth will be pretty narrow on 80 because it's a loaded antenna, but then you can get 80, 40 through 10 with the 67-foot version. And I've experimented, and you can clip on a little piece of wire and let it dangle down, and you can even make it work on 60 meters. It's a very flexible antenna. Not only can you use it on the design bands, but you can mess with it, more technical term, experiment, and use it on all these different other bands as well. Okay, so how do you make your own? First of all, you start by downloading and studying the K1RF presentation. There's a lot of great information there. If you haven't built an infed half-wave before, or you're not a big antenna builder, the ARL has a kit that shows you how to build it, and you get everything you need with it. It's got a one core transformer, and so you can use it at 100 watts. You got to be prepared to trim the length to fit your particular circumstances. I put up a stock infed half-wave in my backyard, and then I had to adjust the length a little bit to get the resonance on 10 meters where I wanted it. No big deal. It was just a few inches. A lot of designs will add a loading coil. It's typically about 6 turns, about 1 inch in diameter, somewhere near the feed point, like 6 feet out or so. And what that does is when you're using the antenna on its higher harmonics, like you've got an 80 through 10 version and you want to use it not only an 80 and 40 and 20, but also 15, you need to add a little bit of inductance so the resonance on 15 meters comes down into the band. Otherwise, it'll be up toward the top of the band. And the reason that is because if you calculate the frequency of a half-wave dipole, that includes the capacitance at the end. Well, when you're using a big antenna on its harmonic, there are no ends on these higher harmonics, and so that effect is lost, and you add this a little tiny bit of inductance. It doesn't affect operation on 80 or 40 meters hardly at all. 20 meters a little bit, but then 15 and 10 meters, it brings the resonant point back down into the part of the band that we like to use. If you're going to build one of these things and you're going to run full power, use 2 or 3 of the 2.4 inch toroids, 2.4 inch outer diameters, particularly if you're going to run FT8, which is a 15 second, 15 minute, that's moon bounce, okay? 15 seconds of transmitting time at high power will heat up ferrite cores. Remember, this is a design where all of the power goes through that core. It's not a choke balance, okay? So you got to make sure the core can handle that amount of power. So at high power, full duty cycle, I would use 3 of these things, but for code and for voice operation, you can use 2 of the 2.4 inch toroids. At 100 watts, you can get by with one of the 1.4 inch toroids, so it's kind of a smaller form factor. And down at QRP, you can just use one of the little 1 inch jobs. Remember, you're going to use type 43 material, and you got to use enameled wire, not bare wire. If you use bare wire, what happens is the wire contacts the core electrically, and the ferrite's electrical resistance will affect the antenna. So use the enameled wire. You can also use wire with plastic insulation on it. Your compensating capacitor, don't be afraid to experiment. It's not particularly critical, but you need to have one. 100 to 100 picofarads, 100 to 150 picofarads is about right. There's a lot of these out there. They're little disc ceramic capacitors, and they should be rated for 3 kilovolts or so. I'm going to jump back here. I think we can see a picture. There it is. This guy right there. That's 150 picofarad, 3 kilovolt capacitor right there, so you get an idea how big they are. There. Okay, so that's basically how you make your own. Now, when you put these things up, watch out for high voltage at the feed point. you're kind of typically used to hooking up your coax to center of a dipole, and that's not a particularly high voltage point, even at substantial power. But on an infed, yep, you're going to get a lot higher voltage there. So you want to make sure that you can't touch it. You want to make sure that people walking around can't touch it. So you want to put some kind of little fence or something around it that says and you just got to be careful about that. Also, if you put it in a tree or up by the tree, the transformer, or the other end of the antenna, that high voltage is enough to cause, it'll actually set leaves on fire. Don't ask me how I learned this. Okay, all those who have set a tree on fire with a wire antenna, raise your hand. Thank you. I was out doing a July 4th parade. I dressed up as Abraham Lincoln and sent the Gettysburg Address on 40 meters. And so we're sitting there waiting for the parade to start. And I thought I'd tune up a little bit and practice. And we had a nice big screwdriver antenna. And I'm sending away, and somebody said, "Hey, there's smoke coming out of the tree." And sure enough, the sycamore was emitting a little fumage there. So you got to be careful. There's plenty of voltage up there. You can install these things as a sloping antenna. You can install them with a center support with the impedance transformer over here, and they go up over the support and then back down the other side. Or you can put them all the way up horizontal. They just want to work. Now, be advised that if you got the transformer up in the air, that outer surface of your coax will be part of the antenna. So expect it to affect the tuning a little bit. But like all of these antennas, the higher you get them, the higher they are in the clear, the higher where that current maximum point is, the better they will radiate and the better they will hear. So it's sort of a trade-off between the aggravation of getting them up mechanically and dealing with whatever electrical effects of the feed line. Okay. Also, just a pro tip here, horizontal antennas, horizontal polarized radio waves have a lot less loss than vertical polarization. And that's particularly important when you're doing a portable operation like parks on the air or something. And if you can, you know, you're going to have a compromise antenna. It's not going to be a fixed station type antenna. So if you can, use horizontal polarization. I know the little loaded whips are, they're convenient, they're easy to set up, and that may be the most important part of your selection. But if you can put up with a horizontal antenna and the various support requirements, you'll get out better. Okay, if you're operating portable and you get some RF in the station, okay, you're on the picnic table and the impedance transformer is just right over there and there's the antenna, or maybe it's going right overhead. You can just coil up some coax right where the coax comes into the operating area. A few turns, 6 to 8 inches in diameter, will put some inductance in that outer shield, and it will help block common mode current, which is what you want to get rid of. Always use good quality coaxial cable. For summits on the air where you're actually carrying it around, that kind of thing. RG174, the sub-miniature stuff that's about 1/10 of an inch in diameter, well, that's just fine. But I don't use it longer than about 25 feet because, hey, it's lossy. And, you know, you're working hard enough with the radio and the battery and everything else. Don't throw away your power if you can help it. RG58 is great for 100 watts. We have a friendly cat. This is Miss Electra, and she says hi. She just wants to get in on the action. RG58 is great for 100 watts up to about 100 feet, but be advised that all these RG numbers here, these are no longer controlled by mil spec. So what you get is anything could be called RG58. There's no rule that it can't be called 58. Spend the money on the coax and get the good stuff from a reputable manufacturer. There's a lot of junk cable out there. If you strip away the jacket and you can see dielectric through the braid, it's not good cable. So get the good stuff. RG8X or RG213 will be fine for higher power, and RG8X and 213 are both available as direct bury. So if you've got a fixed station and you do want to bury that cable on the ground, you can do it. If you don't have direct bury PVC, they're typically going to degrade a lot faster. So for long runs, you want to use the bigger cable. Okay, so let's summarize what I just told you. The infed half wave, it's a half wave dipole on its fundamental, just like every other half wave dipole in the world. You're just feeding it at one end. It's the same antenna as a half wave dipole, center fed, and an off center fed, and an in fed. They're all the same antenna. Okay, they will operate on multiple bands because all those bands have high impedance at the end, and then you can use a well-designed impedance transformer, convert that high impedance down 50 ohms. But you have to check your trade-offs with other dipole type antennas, whether you want to do the off-center fed antenna, whether you want to do the center fed with the tuner or whatever. So basically, it wants to work. It's a dipole. You're just feeding it at a funny place. And so you have to think voltage instead of current. And that drives your design, and it drives your selection. So that is the story, and I am available for questions. Dennis, you going to run that show? Who's got a question?
Okay, you want to lower your desktop?
Oh, yeah, sure. Although I might, let's see, where is the stop? Oh, there it is. Stop sharing button. No. Come on. Oh, stop share. There it is. Okay.
Okay, there you are.
All right. Get rid of that. There we go. Okay.
Okay.
I am a QRV for questions.
Okay, Barry, what we got in chat?
Lots of stuff in the chat. Carol
Ah,
wants to know, can you bury a counterpoise?
okay, let me get the chat up here. Okay, what was the question, Barry?
Can you bury an antenna counterpoise?
Can you bury a counterpoise? Yeah, basically, that's going to couple the antenna to the ground more. Yeah, sure. I just buried my coax that goes out to the impedance transformer, and that was enough. If you electrically connect with bare wire or something like that to the ground, it'll have a different effect than if you just lay insulated wire on the ground. But yeah, there's no reason, there's no giant electrical reason why you can't bury your counterpoise.
Okay. Does it matter how deep to install a ground rod?
The ground rod. No, not really. At RF, most of the effect of the ground rod is within a few inches of the top. For lightning protection, you might need, a couple or 3 feet. Building codes specify 8 feet because they are mostly concerned with 60 hertz and lightning. And so you need the full length of the rod. For antenna stuff, all you need is a foot or two, and even that is overkill. It's mostly a mechanical consideration at that point. You could just get a big nail and point it and poke it into the ground, and that would be just dandy.
Okay. When you say you use the 2 toroids for full power, do you put them together and run the wire through both centers at the same time?
Yes, you stack them right on top of each other. And then what I do is wrap them with electrical tape. You use a good tape, not that cheap 50 cents a roll stuff that they have up by the cash register. Go get the Scotch 33 and wrap them once with electrical tape to hold them all together. Yes, so they need to be together.
Okay, down here, some more.
see,
How would an antenna like that work on VHF, UHF?
I have no idea. Heck,
Okay.
some RF would no doubt leak through the transformer, just the capacitance of the transformer, but it would probably be soaked up quite a bit in the core. And I have no idea what the impedance of the various paths through the transformer would be.
Yeah,
If
Ward,
any RF got to the wire, it would definitely radiate, but I would say
I can actually help you out there. I've tried it.
Way to go, Matt. Bail
A
me out here.
half wave is still a dipole, even on the 70 centimeter band. So the wire part of the antenna works great. But if you go get a type 43 ferrite and wind this transformer and try to use it on 400 megahertz, you have built a space heater. You need a very, very different ferrite composition, much, much smaller. Quite frankly, you're probably going to end up having to make it out of a printed circuit board, trace paths to make it work right at those frequencies.
I think the idea was to use this on both HF and VHF. I don't see the question exactly, but
I haven't seen a transformer that's broad-banded enough to work all the way from 40 or even 20, like even up to 2 meters.
Yeah.
I've built 1,000 of these things, and they are workable with the type 43 ferrite on 6 meters.
Yeah.
If you want to, there's just a couple of things I thought of while you were talking. My end-fed half waves almost all have links in them, so that I can get work bands by connecting and disconnecting pieces of the wire. So the transformer works fine through those frequency ranges. You just have to be able to change the wire length. And I don't know if you're familiar with Larry W0QE. He used to do the Sim Smith tutorials on YouTube. He has a great video discussing magnetically coupled transformers versus auto transformers. And after that, I started winding all of my ununs as auto transformers. I just tap for my feed point and go on. I've got one piece of wire wound around there. And what I find is that the cores don't heat up nearly as much because the coefficient of coupling is so much better in an auto transformer. But
yeah, auto transformers are different. We saw that parallel LC circuit at the bottom of the center of the bobtail. And what you're doing is using the coil as an auto transformer where you're just tapping up along it. Yeah.
Yeah.
Matt, I thought of something. Try this and let me know how it works. If you just took a 19-inch piece of wire and you connected it to the center conductor of the SO239, ignore the transformer and all that stuff. Just connect another piece of wire to it and run that, stick it up vertically. I bet that would work as a ground plane using the coax shield, and it wouldn't even notice the rest of the antenna wouldn't even notice it.
Yeah, no, that works fine on 2 meters. And then just one more little deployment thing, because we are relying on the flux, the magnetic field that develops on this toroid to move the power around. These things often go screwy if you set them directly on the ground. The earth itself will interfere with the magnetic field that develops around the toroid. So they lots of times want to be at least 6 inches up in the air to work consistently.
That's also a capacitive thing. The capacitive coupling between
that too.
Transformer and earth. Don't lay the transformer on the ground. Good point. For lots of reasons.
Yeah.
This cat's trying to drink
my
water.
Here's one that was already answered in the chat. Can you share an electrical system ground rod? And Dave, a residential electrician, said the code requires you to bond all ground rods for residential installation. So you kind of have to do that.
Yeah, the word is shall in DC. There's no wiggle room there.
Right.
Every external earth electrode, whatever it is, shall be bonded together. And that's for lightning protection. And what happens when you have big currents flowing through the earth, And that causes big voltage differences between different electrodes. So that's the story I tell is some guy sitting there in his living room and he's just minding his own business, and a thunderstorm comes through and he sees this big flash, and all of a sudden there's this big green arc that jumps from his antenna system to his telephone or his entertainment system or something, and now nothing works. But they were both grounded. What happened? Well, the grounds weren't connected together. So all that current flowing through the dirt created multiple kilovolts of potential difference between the ground connections. And so just for that tiny little bit of time there, it was enough voltage to cause an arc. So everything outside has to be bonded together. And you get real good at, taking number 6 copper AWG, that's kind of the standard, and putting it on the little acorn clamps or what have you. And if you're going to create a big ground system, well, I'll tell you, I could spend hours talking about this, but it's also this book, which is, 20 something bucks. It's cheaper than one trip to the hardware store, I'll tell you. So get this and get the book and read all about lightning and grounding systems.
Right. Someone wanted to know if an end-fed half wave with a 49-to-1 on 80-meter Arden is out of the question.
Yeah, 80 meters, 49-to-1, end-fed half wave. That's perfect.
Okay. And that's all from the chat, Dan. Dennis, you had your question. Hand up. Did you have a question?
Not a question. I was just going to make a comment when you were talking about just adding a quarter wavelength of wire for 2 meters. It reminded me of sticking a coat hanger, a straightened out coat hanger in the top of a Gonset Communicator 3 back in the day for 2 meters.
Yep.
Maybe
Loading up the
or
bed
one-
springs on 10 meters. It's a classic story. Today is the 1959 of your lives. Now you can go on with your life, and for the rest of your life, you can torment young hams by telling them how great it was in 2024.
I like to point out a little plug here for Warren here. His ham radio for dummies, 4th edition, is available on Amazon in CD form, book form, CD form, Kindle form, and Audible form. I just downloaded my Audible one for my cell phone to listen to it. So I thought that's
I
out
wonder
there.
who read it, or maybe it was an AI text to speech or something like that. They didn't ask me to do that.
They have a person doing all the reading for you, different name than you. So they must have jobbed it out.
I'd like to meet them sometime.
Anyway, if you go look on Amazon, you'll see all those different formats. And I will share a quick story because everybody's doing that. And again, as a teenager years ago, I want to get on. I had an old 2-meter tube radio, and I wanted to get on 2 meters, and I didn't have any money, so I made coat hanger type thing, just like you guys were talking about. And I put it out there, mounted it to the side of the house, it was staple, and it was working great. And at any rate, I was a novice then, so 2 meters was about the only voice I had. And my neighbor come over, and she was telling me jokes. But they were jokes that I had dreamt up, made up as a kid to tell other kids. How did she know? Come to find out is every time it snowed, I was getting into her and who knows else, who else's TV set.
Yeah.
Oh, for good old days.
You learn all kinds of things doing that kind of stuff. That's where the term Tennessee Valley Indians came from, TVI. Back in the day when everybody was on AM, if your signal was picked up by a radio or TV or whatever, and was detected by the circuit, the person whose TV it was could actually hear and understand what you were saying. It wasn't like single sideband, which is like this. It was actually voices. So you had to speak kind of in code, and you didn't want to say, "Hey, I'm interfering with my neighbor's TV, who would just say, hey, I've got some Tennessee Valley Indians here. And it's an interesting thing. With digital TV, television interference has gone away for the most part. The only thing you get now is thumps and bumps and disruptions of a digital communications cable or something like that, or you get into an audio amplifier. But TV interference is a thing of the past, thankfully. And I wanted to mention that Matt there wrote a really nice bunch of information for the handbook. So Matt's a famous handbook author now in chapter 24.
I had a lot of help from the editor.
Yeah, well, thanks a lot for doing it. I really appreciate it. So
Yeah.
And so do your readers, your many loyal readers. So that's good.
Well, since you set me up, I'll do a little shameless self-promotion
There you
here.
go.
Well, I happened to make a video about the auto transformer method of winding a 49-to-1. So I'll post that in the chat since it's relevant.
There
You
go.
want to give a presentation on RATPAC?
You sent me an email and I replied to it, and you haven't answered me and said what you want me to talk about.
Had 50 some odd email replies.
I wasn't going to bring it up, Dan. I
No,
figured
it's
you'd
a
get around to me eventually.
It's a huge problem. And so we have now created a thing, I have to go check it out and such, but people can go in and choose the dates that they want to do it. And if it's been taken, it won't show up because it has been crazy trying to figure out how to take care of all that.
Sure.
50 some odd, and they're still coming in.
Yep.
Hey, I noticed Glenn Martinez has a question. He had his hand up. Glenn, go for it.
Roger, AH6 Victor Foxtrot over in Hawaii. I like your presentation. I jumped in a little bit late. Curiosity, your slides. I was a little slow on doing screen capture on some of them. Are they going to available anywhere, or the slide presentation?
I will send them to Dan, and he can post them as a PDF on the website.
Yes, and all of our YouTubes that we put out there, we give links to the slides and things like that, so that they could. The idea behind what we're doing is to share, so that clubs and individuals can use it for their stuff and pass the word and keep things going.
Okay.
All right. Anybody else?
Appreciate it. Thank you very much.
Bet, Glenn, mahalo.
Someone wants to know, would a Buckmaster offset center fed antenna perform about the same as an end fed antenna?
Yeah, it's trying to do the same thing as an in-fed. It's just fed in the middle somewhere and uses a different impedance transformer. A lot of those impedance transformers are an impedance transformer and then a common mode balun, a choke balun in series to decouple the feed line. And some of them depend on the feed line of the vertical section. I think the Carolina Windham is such a design. It's not really a true Windham, but nobody puts up true Windhams anymore. So whatever, it's a dipole fed with a coax that then acts as a vertical radiator as well.
Okay, it's been a great presentation. We've gone over, but on these kind of presentations, you don't mind going over. Anybody else got any questions?
That's all in the chat. We're good.
Okay, great. All right. Unless we got some more activity out here, I'm going to pull the plug, call 73s, and see you all next week. I really appreciate you doing this. And for those that's trying to get on RATPAC, we're working on it. It's really been I think we have a system now that might help everybody.
Okay. All right.
Thank you all
for the invitation, and we'll see you next time.
See you next time, 73s.